Okay, let's do some circuit analysis. Let's look at the circuit and find out what does it do, how does it work. Okay, first here we have a high priority encoder. It's an 8 to 3 priority encoder, high priority encoder. This E1 here is the enable input. It has to be 0 here in order to have the chip working. E out here is the validity output. This is equal to 1 if any of the inputs is active. That means that the output is a valid output. Okay, if you look at the input here, you see that the first input is connected to ground along with the inputs 6 and 7, while inputs 1 to 5 are connected to switches. All right, the output, which is the code that represents one of the input, is taken into the P input of 4-bit comparator. This device here, it compares the 4 bits P, 0, 1, 2, and 3 with the 4 bits Q, 0, 1, 2, and 3. Now, the outputs of the priority encoder, as you know, here it's equal to 1 if the P input is less than the Q input. Here, this is equal to 1 if they are equal. And here it's equal to 1 if P input is greater than the Q input. Now, the code that is received here is what's the output of the priority encoder. What are the possible values for the code at the output here? It's the code for the input 1, which is 1, 0, 0, or the code for the input 2, which is 0, 1, 0, or the code for the input 3, which is 1, 1, 0, or the code for input 4, 0, 0, 1, or the code for the input 5, which is 1, 0, 1. It cannot be the code for 6 or 7 or 0 because they are grounded. And this is a high priority encoder. So the value that is received at the P input of the comparator is something between 1 and 5 in decimal, or the binary representation 1 and 5, because P3 is connected to ground. Now, if we look at this input, we find out that it has a fixed value, which is equal to 0, 0, 1, 0, which means Q has a value of 4. So this has a value between 1 and 5. This has a fixed value, which is 4. If switch 1 or 2 or 3 is switched, okay, that means P here is less than Q, which means this output will go out. And if this output go out to the NAND gate here, E0 is equal to 1. That means the output of the NAND gate is 0. That means this yellow light will light up because here we have a high voltage and here we have a ground. So this LED will light up if any of the switches 1, 2, or 3 is pressed, because this will end up that this P is less than 4. So this output will go out. Now, if switch 4 is active, what we will have here is 4. And 4 is equal to 4. So this output will come out to be 1, which will make this 0, which will make this light go on. The red light here will go on if switch 4 is active. Also, if switch 5 is active, that means this here will be greater than the Q, because this will be 5 and this will be 4, and this is the output that will be activated. It will be 1, which will make this output here 0, which will make the red light turn on. The reason that we connected the validity output to this NAND gate, because of the case where none of the switches is pressed. That means here we will have 0, 0, 0, and this will be less than that, and this will go on. But this one will not go on because this is not a valid code. So this will be a 0, which will turn this one into a 1, and this will keep this light off. Otherwise, if we connected this directly to the LED, this case will cause this LED to light up even if none of the switches are active, and we do not want that. Okay, let's look at this circuit. The circuit here implements a function H, which has a domain X, Y, Z. Note that X is the select line of this multiplexer, and Z and Y are the select lines for this decoder. What is H? As a function of the inputs X, Y, and Z. Okay, this is a decoder. What is the output here? You remember the equation for the decoder. The output here is S0 bar, S1 bar. S0 bar, S1 bar. These are the select lines. So the output here will be Y bar, Z bar. Notice that Y is the most significant. Instead of S1, Z is replacing S0. What will be the output here? The output here will be YZ bar, okay, which is the output number 2. What will H be equal to? Remember, this is a multiplexer. What is the equation of this multiplexer? It's equal to I0 S bar. I0 is this, Y bar, Z bar. Y bar, Z bar. S is equal to X, so it's X bar. ORed with X, I1. X, Y, Z bar. X, Y, Z bar. And from here you see that this is minterm 0 and this is minterm 6. So H is equal to the sum of minterms M0, M6. Okay, suppose that you were asked to implement the function W with the domain ABC, sum of minterms 0 to 5, 6, using a 3 to 8 decoder. What you would do is you will connect the domain to the select lines of the decoder. C being the least significant, so you connect C to S0, and then you connect B to S1, then you connect A as the most significant to S2. Suppose mistakenly you connected C to S2 and A to S1. When this mistake will be exposed? Minterm 0 is when A, B, C are all zeros. Okay, this is 0, this is 0, this is 0. When this minterm occurs, what happens is that the output 0 will come out to be 1, so W is equal to 1. So this is okay. When minterm 2 comes in, this is C0, B1, and A0. Okay, here is 0, 1, 0. This will lead to this output going out, making W equal to 1. That's fine. For the minterm 5, C is equal to 1, B equal to 0, and A equals to 1. This will make this output active, which will make W equal to 1. So this is all right again. In this minterm, which is minterm 6, C will be equal to 0, and B equal to 1, and A equal to 1. But actually here, 1, 1, 0 will make this output goes to 1 instead of this output. So W will not come out to be equal to 1. So in this case, only when minterm 6 comes in, the mistake will be noted. Okay, the circuit below implements the Boolean function f with the domain x, y, z. Here we have x, y, and z. What is f at the output? Remember, this is a decoder. Remember the equation of the decoder. here we will have S0 bar, S1 bar, meaning X bar, Y bar at the output. This output here will be X bar, Y. And this output here will be XY. Now, these two will go into this OR gate, and here they will give me a Y. And now, this is a decoder again. So the output here is equal to Z bar Y. This is Y, and this is Z, so Z bar Y. Now the output of this OR gate is the function, which is equal to this. And if you expand this into sum of minterms, you will get M0, M1, M2, and M6. Okay, use 2 to 4 decoder and AND gates to design a 1 to 4 demultiplexer. Remember the equations for the demultiplexer. The output of the demultiplexer is equal to the input D ANDed with S0 bar, S1 bar. And Y1 is equal to this, Y2 is equal to this, Y3 is equal to this. So what we need is a decoder, 2 to 4 decoder, and these are the outputs. Here, take this output and AND it with D. Connect it to an AND gate with the input D. The same with this, the same with this, the same with this. So you need 4 AND gates. This is 1, 2, 3, and 4. Okay, and this is the input D that is ANDed with the output of the decoder. This circuit here, complete circuit, is a 1 to 4 demultiplexer. This is the input, and these are the output of the multiplexer, and these are the 2 select lines for the demultiplexer. Use the enable input to expand this 4 to 1 multiplexer, expand it into 8 to 1 multiplexer. Use the enable. Okay, the 8 to 1 multiplexer needs 3 select lines. This one has 2 select lines. We use this one as the third select line by connecting the 2 multiplexers this way. This is the first multiplexer with this. Okay, the select lines are common here, S0 and S1. They are common on both. S2 is connected this way, okay, and inverted to the other multiplexer. So here we have the outputs of the multiplexer coming from the input I0, I1, I2, and I3, and the output here will come from I4, I5, I6, and I7. And then we make an OR gate, taking the output of this one and the output of this one into an OR gate so that just one output is coming out. So this is the multiplexer needed. It has 3 select lines, these 2, which are common, and this, the most significant bit of the select lines.